All right, welcome back. So let's keep our journey, continue to talk about the gradient descent. And I think last time we ended here with the summary for the gradient descent algorithm. Okay, so let's do a refresh for now. I'll keep in mind that our goal is to find the parameters, find the values to the parameters that minimize the cost function. Okay, there's a cost function that we defined in that we wrote as j of theta 1, j of theta and theta 0. Okay, and then we wish to find the points within the space of theta, and we wish to reach the minimal point that's give us the minimal value for the cost function. Okay. And the algorithm look like this. We will start with some initial values for theta 0. So we will repeat the following steps. First, we compute the gradients of the cost function with respect to all thetas. Okay, so let's look at the term gradient again. So in nature, the gradients of some function is basically the partial derivatives of that function with respect to all components of thetas. Okay, and then we will use these gradients to update the theta. Okay, so the way we update theta is to use the old value of theta minus alpha times the gradients. That is because gradients points to the direction that the function increases with the maximum speed, with the maximum rate. So if we minus the gradients, it will actually make the changes along the opposite direction, which is the fast decreasing direction, which makes us find the best way to the minimal point. Okay, and this alpha, which is also we call the learning rate, is also important because not all alphas work perfectly good. Because if we take it, sometimes we take it too big a step, we will miss the minimum points. Okay. So in the programming assignments for linear regression, we will have some optional experiments over the possible values for alpha. You can experiment with, like, the learning process, the learning outcome would be different if we use different learning rates. All right. So the theta that we obtained through this gradient descent algorithm is so will be the optimal, will be the final values, final parameters that we will use for the linear model. All right, so now let's take a look at the gradient descent for linear regression. So all the slides before are general introduction to gradient descents. And now our cost function for linear regression, it is well defined. Okay, it is defined in the form of mean square errors. And let's see how this specific type of cost function can be computed for the gradient descent algorithm. All right, so if we just look at two parameters, theta 0 and theta 1, it's basically this way. Okay, the sum up with the summation of all squared errors divided by 2 times n. And in gradient descent, we need to start with some initialized values. For example, theta 0 equals 0, theta 1 for 0 as well. Now we need to update the theta using the gradients. Okay, so this step is not basically the same as the general gradient descent. So let's look at the function of it. Right, if we expand it a little bit, so the key is to compute the gradients, which is to compute the partial derivatives, which we already know, right? Because we for the normal equation parts, we also need to derive the form of the partial derivatives, and we basically need to do the same thing here. So here, after we take the derivatives with respect to theta 1, this is something that we will have. And for theta, that's for theta 0. And for theta 1, we will have something like this. Okay, and it's actually, if you get familiar with it, it's actually quite easy to memorize, because for theta 0, it's just the differences between the predicted y hats minus the difference between the predicted value and the actual values. Okay, and sum up all those differences. And right here, it is predicted the same difference weighted by the feature, the corresponding feature x. Okay, and this is something we need to use to compute the updates, to conduct the updates, right? Use the gradients computed here. We need to use it to update the theta 0 and theta 1 respectively. And
is the x in the second equation still part of the sum?
Yes.
Okay, cool. Just wanted to verify. Thanks.
Yeah, it is part of the sum, yes. So at each iteration, this is a technical detail that we need to pay attention to, because we need to update the theta 0 and theta 1 simultaneously. Okay, that is said, when we compute implement it with the programming languages, we need to store the candidates or the new values for theta 0, for example, into some temporary variable called theta temporary 0, and the theta 1 into some temporary variable theta 1. Okay, so this is because we don't want the computation of we don't want update theta 0 before theta 1 can be used again, or maybe I should say, we want all the parameters to be updated simultaneously, because if some parameters got updated first, it will influence the computation of the other parameters. Okay, we want all the gradients to be updated at the same time. Okay, we don't want we don't want the parameters that get updated first to interfere the computation of the gradients for later parameters. So this is something that we should know about, at least, though nowadays in machine learning frameworks, we don't actually need to worry about the details too much. Okay. All right, so that is the example only for simple linear models that has theta 0 and theta 1. Okay, but now let's look at a little bit complex case for multiple linear regression, which has multiple parameters from theta 1 to theta n. So this is how the cost function look like. And for gradients, it's actually more or less the same thing that we need to compute. For theta 0, the partial derivatives with respect to theta 0 look like this. For theta 1, it looks like this. Theta 2 looks like this. Until theta n, it looks like this. Okay, so all we need to pay attention to is that the parts within the parentheses, they are actually the same. It's just the y hat minus the y. Okay, the difference is that for theta, the common that is a common pattern, and the outside term, this x1, x2, xn, they are inside. They're still inside the summation operation, but the subscript 1 corresponds to the parameter 1. The subscript 2 corresponds to the parameter 2 here. Okay, so it's basically we use the feature as a weight for the amount of updates needed for the parameter. Okay, so that also makes sense, because if the feature x1 feature, for example, this is the feature for size. Okay, then if the size is already very big, then of course we will need to update the parameters for the size a little bigger. Okay, so these forms for the gradients also are quite straightforward to memorize. Okay, so if we write it as a short form, we can use y hat to indicate the longer equations. Okay, and the updates is the same process that we need to follow as compared to the simple linear regressions. We basically need to update them simultaneously. Okay, and some common practices. Let's see. So far, everything before this slide are about using the second method, gradient descent, to train the linear regression models, and those will be the second part for the programming assignment for assignment 2. So after the lecture is done, maybe I can spend some time on showing on how to run the code, execute the code for the assignment 2, if we have time today. Okay. All right. So since this is our first time introduced gradient descent, and this is actually quite nowadays quite most commonly used way to train a large scale machine learning models, and there are a lot of very practical techniques, common practice that are commonly used in the field. And here I just want to have some quick peek of what these techniques are actually about. Okay, we will have a more systematic introduction as we enter the neural network chapter. But for now, let's just look at what kind of techniques are involved here. So first of all, these are all practical questions, because in order to jumpstart the gradient descent, we need to start with some theta 0. Okay, and then usually speaking, we start with random initialization. Okay, because we don't have a lot of information about the model, about the possible space for parameters yet. And another question is also important, that is when to stop. Okay, so in the pseudocode, in the description of the algorithm, we only said we will repeat the steps until we are satisfied, and that is actually a quite vague expression. So what do we mean by satisfied? So we need to determine the termination conditions. And the third point is, how big is each step? That is, how much learning rate we should set for each step in order to get to the optimal, get to the minimum points as fast as possible. Okay.
So can I ask a question regarding that?
Yeah.
Can you change how quickly you are learning? Like when you first start, you're taking really big steps and then take tinier steps as you get closer to a solution?
Yeah.
Or is that just not practiced?
That is
Okay,
actually
cool.
a common practice. Yeah, that's a very good point.
Okay.
So we usually speaking, we will start with some initial learning rates, and as the training goes on, we need to adjust the learning rates in order to converge to the minimum point.
Makes sense. Thank you.
So like when we the fourth point is like when we have a very large training data sets. So how many data that we should actually include into each iteration, okay? Because if we include too much, or if we include all the training data, that is not actually feasible, because the CPU or the GPU we use can only handle a limited amount of data, can only conduct limited amounts of computation, okay? But if we included too few data points, then the gradients computed from that small subsets of data is not accurate at all, okay? Which will makes the training much more difficult, okay? So for that, we will need to talk about several different types of gradient descent. All right, so in terms of the question of when to stop, we can have different types of termination conditions. For example, we can stop when some predefined number of iterations is reached. That is usually, this way is usually used when we don't actually know too much about the problem. Okay, we just set some random numbers and to say, let's see how good this model can be. All right. So another technique called early stop is something we can use when we want to avoid the overfitting problem. And overfitting is something that we will introduce in the next lecture. So we basically don't want the model to be to know the training data too well. Like it's memorizing every details about the training data and try to make as good predictions as possible, because that will limit the model in terms of its general predicting power. Okay, so early stop can help us to make the training much makes the model trained much powerful. And one common practice is that we will observe the magnitude of gradients. So if the gradients is close enough to zero, so that means we didn't get a lot of significant updates for the parameters, which is a sign to say that the parameters are approaching a minimum points. And then we can, of course, stop at a certain point. For example, we can set a predetermined small value epsilon to indicate that this is the threshold for meaningful updates. Or we can also set a threshold for the cost function. So these cost function and the gradients, they are based on two different thoughts. So because ultimately we want to minimize the cost function, so we can also measure the cost function, how much the cost function changes, right? If the cost function doesn't change significantly, then it's approaching the minimum points. Is something we can claim. Okay. So, but basically these two are commonly used since they based on the observation of the magnitudes of the related variables in the training. Okay. All right. So actually, the most valid way, I would say, is that we need to validate the training performance using some external data or using some validation data after a certain amount of iterations with a fixed amount of iterations, because using a validation set that is different from the training sets will make the model more robust to unseen or unobserved data sets. Okay, so usually we can use this performance as a threshold to decide when to stop, especially when the data is really big. And I have a question that which one is better in terms of gradient versus cost function. So I think a little bit, my own experience is that people seem in the field seem to use the cost function more often. But altogether, they will combine the, for example, the most typical way is to plot the cost function. Or if I use the term loss, it is more commonly used in the field. So people will usually plot the loss with training iterations, okay? And also together, they will also plot, people will plot the performance on the validation data set, which is the validation accuracy, okay. But usually speaking, these two are not within the same scale, but it's a pretty common way to visualize it and determine the points that's how many training iteration we will need. See the points, isn't the gradient just to be attempting to minimize the cost? Yeah, the gradient, the gradients is the amount of change on the parameters that we intend to make. Okay, so if that amount of change is becoming smaller and smaller, and which doesn't make significant amount change to the parameters, then that is a sign to indicate, okay, perhaps we are approaching the minimum points really closely. So that doesn't make a lot of significant performance if we make that change. And that is the basic thought behind why we can use the magnitudes of gradients to decide when to stop. So when the gradients approaches zero, yeah. So in theory, it will never approach the zero if we only use a small, if we are using mini batch, as we will see later. But the cost will the cost function near the minimum points will be its minimal value, which means the cost will stabilize, will not make significant changes. But the cost is not, I would say it's not zero, because the cost is defined as the mean square errors in the case of linear regression. Okay. The positive correlation between costs and the gradients, that's a good point. I don't think in general the trend is a positive correlation, but I won't be very confident if I say there's a necessary positive correlation before these two variables. Yeah, I need to look into that, but it's a general trend that because when we approaching the minimum points, then because the cost function never changes, and in theory the gradients near this more flat region indeed should be smaller, right? Yeah. So I think there will be a slide talking about these points. So when we are approaching the minimum points, because the parameter space is very flat, then the gradients will be very small. And we need to make adjustments to the learning rates as well in order to keep a reasonable step of updates without moving too big a step to suddenly step outside the minimal the minimal point, to miss the minimal point. Okay. All right. A second key point is how we set the learning rates alpha. Okay, so let's again use this plot to show the example. Like when alpha is too big, right? When we start from theta 0, but if we move, because the minimum point is here, if we move too much to theta 1, then we are actually missing the minimal points, right? And if we from theta 1 to theta 0, it will even make us a bigger mistake, right? So this oscillation is something that we want to avoid, right? We want to set reasonable amount of values for the alpha, okay? But if it's too small, which means our training would be really slow, okay? It's taking too long from the initial position of theta 0 to the minimal point. So speaking from the efficiency, that is also something we want to avoid. Okay. So we have the question of how to select and how to adapt to learning rates. So I would say the selection of the initial values are really empirical. Okay, it's really depends on the cost function, depends on what type of learning problems we're talking about. Okay, and usually we don't want to use a too big or too small alpha rates. So usually a learning rate of alpha equals 0.01 is usually a reasonable initial value. Okay, and another point here is that during the training process we need to adjust the magnitudes of learning rates because the gradients get smaller as it approaches the minimum. Okay, and it's even really close to 0 at exactly the minimum point. So in general, we need to decay the learning rates in order to approach the minimum points as close as possible. Okay, if during the late state, during the when we are really close to the minimum points, if we still take a very large learning rate step, if we take too large a step, we are very likely to oscillate around the minimum point without showing a convergent trend. Okay, so there are several types of learning rate decay. Okay, so here there's a sentence that except for batch gradient descent, we'll see what this means. Okay, in the next few slides. All right, so first of all, the time-based decay, which basically lets alpha decay over in a perfect that in a way that decreases with the number of iterations. Okay, so in the later, as the number of iterations grows, the alpha can decay in this way, right? Or in exponential decay, which is also a common choice. Okay, and so if alpha doesn't decay, this is an open question. But basically speaking, the decay of alpha is a default options in most of the common machine learning frameworks now, and we can easily set the ways of decay and how we adjust the rates of learning rate decay. All right. Now let's look at the types of gradient descent, because in the previous slide we mentioned bit about some batch gradient descent. So let's now look at what this means to us. The first type is called batch gradient descent. Okay, it means that we compute the gradients using all data on each iteration and then perform the parameters updates. Okay, so we can imagine that this is really expensive. Okay, if the data set is really big. So the examples we shown in the for linear regression and also for the assignments we are doing for this time, we are actually using batch gradient descent. Okay, so this summation over I means that when we are computing the gradients or the partial derivatives for theta 0, we have actually included all the data points in the training sets. Okay, and the advantage is that because we used all the information, we used all the data points, we are guaranteed to converge to the minimum point. Okay, which means that if it's okay even if we keep the learning rates the learning rates constant doesn't change. We didn't, even if we don't adjust the learning rates at all, it will still convert to the theoretical minimum points. Okay, but the cost is that we need to do a lot of computation in each iteration, right? So it becomes a problem if our training data is very big. Okay, so we got to think about a method to overcome this slow training problem, and the straightforward solution is that we don't use that many data in each iteration. Okay, we can just use part of it or a small subset of it. Okay, so this is the so-called mini batch gradient descent method. So we can set a batch size to decide how many data points are used to compute the gradients. So here, the summation of I at this step actually is not over 1 to m, but over excuse me, but it is over the mini batch of data. Okay, the size of mini batch that we chose to use. So of course the advantage is that it's faster to compute one iteration. Okay, and one common practice is that we should randomly shuffle the data so that the redundant examples are avoided in each iteration. Okay, but also the disadvantages is there because in theory it will never converge. Okay, because the cost function J is actually defined over all the data sets, over all the data points, right? In terms of in the case of linear regression, we are the J is defined over all the mean square. It's the mean square errors over all the data points, right? So if we update the cost function with some parameter, with some gradients that are computed within the subsets of the data, which means this is not the accurate one. Okay, the cost function will not the gradients provided by mini batch gradient descent will not lead to the theoretical minimal points, but only towards some area around the minimal area, around the minimal points. Okay, so in this case, because the gradient is not accurate, we need to adjust the learning rate so that we can guide the gradients or guide the cost function towards the minimum points more successfully. Okay, we don't want the gradient, we don't want the cost function to wander around too much. Okay, and usually if we observe how the cost changes over time, these two methods will show significant differences. If it's a batch gradient descent that utilizes all data, then we should observe a pretty smooth curve, okay? Because the cost points to the theoretical minimum points, and if we are using mini batch gradient descent, oops, then there's some more randomness in the curve, okay? Because the gradients computed by the mini batch is not does not point to the minimum points accurately. Okay, it is not precisely the theoretical gradient, optimal gradients, but it is somewhere close. Okay. Okay, I think we have one more slide for the stochastic gradient descent. Okay, so this is one of the most interesting case, or a special case. Okay, so it uses only one example from data to compute the gradients and to perform updates. Okay, so this is a special case because there's a lot of randomness. When we compute the gradients, there's only one data training example used, which can contain a lot of random factors, right? So the advantage is that it's quite fast to compute each training example, to compute each training iteration, but it's much more noisier because we didn't aggregate information together. Okay, and honestly, we don't actually use this method a lot. Okay, although if you look into the machine learning frameworks, they're usually optimizers defined statistical gradient descent methods described for you, defined for you. Which, if, for example, in PyTorch, there's a class called SGD, which is a method for computing gradient descent automatically. But in the SGD method of PyTorch, it's actually based on mini batch. Okay, it's not a method that actually uses one instance at all. But that's something you can change. You can always tell the computers to tell the program to use only one training instance at a time. Okay, but in practice, we don't actually do that. All right, so if we compare the three gradient descent methods, and if we imagine or draw a how we are approaching the minimum points in the parameter space, you can think of the batch gradient descent in the blue color. It's basically what it meant by sound. Can you be more specific to the question? Did I mention that? Noisy. Okay. So let me go back. All right, I think the current slide will be fine. So the noisy, I mean that, for example, in the stochastic gradient descent here, we will start from somewhere here. We'll start from somewhere here, and the updates given by one data example may point to a totally different direction. It may point to a direction that even deviates from the minimal points. Okay, and then but the general trend is which is that after you have used after you have updates the parameters for multiple iterations, it will eventually approaching the minimal points. But since in each time we only have one data example, and in one data example doesn't represent the whole training data sets. Okay, each data example may point to a direction that deviates from the minimum points of the cost function. The cost function is defined against all data examples. But if we use the gradients computed from one example, that is not necessarily that gradients does not necessarily point to the minimum points of all defined over all data points. So that is basically what I mean by noisy. So it is the path of how we approach from the initial position, that's our theta 0, to the minimum point theta n. Okay, so the path would be much more zigzags in the path. Okay, and the batch gradient descents. Okay, on the other way, it's in each iteration it uses all the data points to compute the gradients. So it is quite an accurate estimation, right? It's just directly to points to the for example, in this case, we start from here. The first iteration will give us this blue arrow that points to the direction to the minimal points, and this direction is perpendicular to the current to this curve, which is the which describes the space of the parameters. Okay.
So in batch gradient descent, is there no noise because it's always moving closer to the minimum value?
Yes, that is correct.
Okay.
Yeah. Is the direction of the arrows based on the rate of change and derivatives? Yeah, the direction shown here in the arrow by the arrow is the direction of the it's the opposite direction of the gradients. It is exactly how we change the parameters. Yeah. Okay. All right. So this is another analogy to how you choose the skiing path. So the batch is in the middle. You're basically going towards the minimum points, but that is sometimes not that cost efficient because you want to spend too much time in each iteration. And the mini batch is somewhere in between these two options because we will choose a reasonable amount of training data at each iteration with a little cost of losing some accuracy, right? But with a lot of advantage in training the model in a quick style, in a fast style. All right. All right, so some other tricks in training. First of all, we should almost always normalize the data, okay, before we feed the data into a model, okay. So by normalize the data, we can use a typical way, which is to subtract the mean values for each feature and divide it by the standard deviation or the variance of the data, okay, because it will make all the features to the similar scale, okay. So without normalization, if we plot the so the data so the data would two features of data would have very different scales if we don't normalize them, and the resulting the resulting parameter space would also be a distorted, like distorted ellipse. It's not like a circle with contours that are like all circles around with same rate of change along all directions. Okay, so in these distorted contours, it will be much more difficult to train the model, because if you start from somewhere here, then in each iteration, the gradients will point to the direction that is perpendicular to the contour, okay, which means there will be a lot of zigzags. So the total steps would be much longer to converge compared to the normalized version. In the normalized version, as indicated by these circles altogether, these all the contours are like very beautiful circles. Then if you compute the gradients direction, the direction of the gradients will be directly pointed to the minimal points. So normalizing data will make the training much easier. If we want to have a short take-home message here. All right. The last page for a recap of gradient descent. So hope this slide can summarize the first assignment, the second assignment for linear regression. And let me see if we can look at the codes for the assignment for now. Maybe some explanations can help you better quickly start it. Okay, let me pause the. Okay, so for these assignments, we actually have two parts of practice. So first of all, the data. If you look at data, it has 3 columns, right? The first 2 columns are the features. 2 features. We use the 2 features to predict the last column. Okay, and some places you may pay attention to is here. When you import a package, we will use the matplotlib to plot the curves, and this library will be used a lot in the future. So if you don't have it, you need to install it. If you install your Python in Anaconda, you probably already have it. Okay. And when we load the data from the CSV file, we directly open it here. So you need to make sure that your data file is included. The data CSV file is in the same folder as your assignment 2 notebook. Okay. So this step of code actually do the normalization part, and this kind of normalization is not exactly the way that we introduce in the slides, because in the slide we need to center all the data with the around the mean values and divided by the standard deviations. So I think I just somehow just didn't do that implementation, but I don't think it's will influence our outcome really a lot. All right, so for the first task is to implement the normal equation method for linear regression. Okay, and it's basically returned by this equation here. Okay, so you need to call the dot products and the inverse computation provided by NumPy. And after the details are learned, you can also use this equation to make the predictions. So it asks for you to compute the residual sum of squares of the model, which is the squares of the distance between the predicted values and the actual values. Okay. And the values will be stored in here in RSS in the residual sum of square are 1 here, RSS 1 here, it will be compared to the later RSS 2. All right. So for the cost function, for the gradient descent part, which is the second task, you need to implement it. First of all, the cost function. Okay, the cost function is like this, and the gradients can be computed with these equations. Okay, so there are 3 components. Okay, so the gradients is actually a vector that has 3 elements. Okay, the first element is the gradients for theta 0. Okay, the second is theta 1. The third is theta 2. Okay, and we define the way to compute gradient descents in gradient descent function here. And within this function, the function will take into the data x and y as inputs. And the values for theta, right? The theta is the original parameters, and alpha is the learning rates. And the number of iterations is the total number of iterations we want to do. Okay, and the returned value is a tuple of 3 elements, which is the theta, which is the learned parameters, which is after that many number of iterations, what is the ultimate parameters we learned. Okay, and RSS and the cost array. So the cost array store the cost value for each iteration, which will be used for the plot step. Okay. All right. So there's a for loop here. Within this for loop, we need to do one iteration for the gradient descents. Okay. So basically, we need to compute the y hat. Okay. And the result of y hat is an n by 1 matrix. Okay, so you can refer to the previous step here. Y hat is computed by x times theta. Okay, to help you implement it with numpy. Oops. Okay, and the difference is the difference between the predicted y hat and the actual label, which is will be indicated by here, by this equation. Okay. And the cost.
Wait, is it all 3 equations or just the first one?
You need to implement all 3 equations.
Is equal to 1 value, or is diff?
Yeah, 1 value can be a vector.
Oh, okay, cool.
Yeah. The cost function is basically computed using this formula, but also using the difference defined that you implemented here. Okay, and after the cost, so cost is a number here. Cost is just a quantity, and after the cost is computed, you can append the cost into the array, cost.array. Okay. And the next important step is to compute the gradients. Okay. And I have a hint here that gradients is the same as theta. So because the theta is a vector of 3 elements, you should also implement gradients in a way that it's also a numpy array of the same number of elements. Okay, so after the theta, after gradients are implemented, you can use one statement to update the theta. Okay, so it's basically theta minus alpha times the gradients. Okay, all right. So after these 4 loops, the theta are already updated, and you can use theta to compute the y hats and also compute the RSS and return them in the final statements. All right. So one additional hint I can give for now is that you should use the summation and the dots instead of using for loops in Python. Okay. So, for example, when you sum up these the summation of this difference and the first feature, because I ranges 1 to m, it's basically a dot product, okay, between two vectors. And the I minus y hat minus y is a difference vector, okay, and the x1 is also a long vector, okay. It is a column vector that has m features in it, that has m data examples in it. So I would encourage you to do some experiments on different ways of the combination, so that everything is implemented in the vectorized style, okay, so that the computation is optimized, is really fast, and not implemented with Python for loops. All right, and after the two tasks are done, there's a third task that asks you to experiment with different alpha. So for here, you feel free to do the experiments, and there's no expected output for the task 3 because there's no standard answers here. Okay. Yeah, we need to do the 1 over m within each pop it out of the summation. So we do need to do the 1 over m. Let me see. Yeah, you need to use the m because the m is computed here. Yeah, the cost function. In the cost function, you need to use the 1 over m, 1 over 2m here. Yeah. And for the gradients, there's also 1 over m here. Okay. All right, so I think we are pretty much done for the linear regression models. Yeah, we're computing those 3 equations for each iteration of the loop. That's correct. Let me see. I don't think we have more quiz questions today. Yeah, there will be no quiz questions today. Okay, so I think that's pretty much of it for linear regression models. And for the next lecture, we will start talking about logistic regression. Okay, so strictly speaking, linear regression model is not a it's predicting a continuous value. It's predicting a number, right? But in most of the cases that we want to predict the categorical variables, whether a picture is a cat or dog, whether the answer is yes or no, like or versus not like, all those categorical variables can be approach using logistic regression models. So from the next lecture on, we'll start talking about that model, and there will be new assignments, but in a pretty similar style of the linear regression, in which we implement the gradient descent methods as well. Okay. So in mini batch, that's a good question. In mini batch gradient descent, the size of the batch size is usually defined in a way that the data can fit into the memory of a computer well, and also we usually choose numbers such as 64, 128, so that they can be optimized by the CPU conducting the computation. Okay, but it's really an empirical value that's different. For example, if your model is a huge model, then the batch size can be a smaller one, like 8, 16. All these can be possible.
Professor, but does that depend on CPU size? I mean, memory size?
Yes. So you don't want your batch size to be too big so that it breaks your memory or your CPU or your memory or GPU memory.
Okay. Okay. Thank you.
Mm-hmm. All right. So.
Professor, I had a quick question.
Yes.
So when we're running predictions and training models, why is it always that we need like a really fast GPU, like a 3090 or something, if all of these aren't these most, like, what graphics are we processing? Wouldn't most of our processing power come from our CPU?
Mm-hmm. So that's a good question. So I think I can better answer that when we have started talking about computation graphs. But if I briefly talk about it, you can already have a sense of it, because so far the computation that we used a lot are the matrix multiplications. For example, if you want to make a prediction, which is a matrix multiply a vector. Okay, so these computations is basically the product between numbers, the multiplication between numbers, a lot of numbers, and to sum up all these products. Okay, so these multiplications can be conducted in parallel within the GPU. Okay, so within the circuits of GPU, they have these sort of optimizations so that a lot of computations can be a lot of multiplication operations can be conducted in parallel, and those computation are really much faster than the way if we do it in the CPU, because CPU is good at sequential operations, but it's not parallelized. Okay, so for most of the matrix multiplication, we need to use GPU to yeah, it's a kind of parallel computation for matrix multiplication or other vectorized operations.
Perfect, thank you.
Yeah. So I think we're talking about, so the concept of parallel computation, it has a lot of different, if we're thinking of it from different scales. So GPU based computation can also be parallel. If we have multi-core GPUs, we can of course make up multiple threads, make up multiple processes to do the computation. But the GPU is some built-in optimization for computing numerical vectors, for computing the computation between two vectors or between two matrices. These are internally optimized for GPU. Allows for computations on vectorized functions and parameters. Yeah, so CPU can also do the vectorized computation, okay? But the CPU is something you can think of as a water hole that is really thin, okay? But the GPU is a water hole that is really thick, that allows a lot of waters to pass through at the same time, okay? But for this class, yeah, that is something we've been talking about a lot within the departments, because for this class we don't have a lab session. So in theory, if we have labs that has some GPUs installed, we would be better, would have better experience when we run larger models that involves a lot of matrix multiplications. For example, in a deep neural network, when you have a model that's really large, it'll take forever if you run it in GPU mode. Okay, but with the CPU, it'll take a lot of time in CPU. But with the GPU, we're able to experiment with more models, larger models, and fancier applications. And but unfortunately, we for this class we don't have those setups. We don't have lab setups. So for most of the assignments, in the future assignments, we will experiment something with deep neural networks, but we won't be based on actual data, right? The assignments won't be based on actual data. Yeah, Google Colab is a good place for you to play around with GPUs. 380, yeah, 380 is the kind of the state of arts NVIDIA. What decides whether the CPU or GPU is being used for computation? So in computer, in our computer program frameworks, if we use PyTorch in the future, there's a very convenient way to set up the way you use CPU versus GPU. So first of all, if you use NVIDIA 380, like basically most of the GPU-based computation needs to utilize the NVIDIA graphic card, and they will ask you to install drivers and the computer the programming runtime package called CUDA, supported by NVIDIA. You need to install CUDA in order to interact with GPU, in order to copy data to GPU, get the computation done, and copy the results out. Okay, so in Python we can interact with CUDA quite easily. Okay, so in PyTorch, in TensorFlow, it's very easy to specify, to tell the program that I want this matrix to be stored in GPU, and I want these parts of computation to occur in GPU. Those are all very easy to implement nowadays. Yeah, CUDA needs to be installed. CUDA supports, CUDA can be installed to Windows or Linux. And if you have a desktop that has 370 or 380 already installed, then you can try it. In Windows, I think it's quite easy. And in Linux, if you're experimenting with it, you can also spend some time to do that. But on Mac, it doesn't currently support CUDA. 980, I haven't tried that. Can probably also get some performance advantage over CPU, I think. At least in my lab, I have 1080. I have 1080, which is like years ago, but it's still sharp. Yeah. Yeah. if you have already CUDA installed, and you can play around with really cool applications, actually. Yeah. 970. Alrighty. 1660. Don't know. I don't know. Never tried that. So it's still GeForce, right? I think GeForce is supported by CUDA. Yeah. Alrighty, I think I will stop sharing and stop recording.